I was going to start today with the moisture lecture, and then next week on Monday, since we moved the exam, I'll come back and finish IR and just introduce proximate analysis in general, and probably answer some of your questions if you have any questions on for the exam. Walter.
So, what does the exam cover up to again?
Everything up until IR. Nothing including moisture or proximate, nothing.
Oh, but
It won't include.
it includes IR though?
It includes IR because we covered most of it. I'll just finish it on Monday. Yes, okay. Yeah. With that,
Okay,
Ted is on.
all right. So some of you had part of what I'm going to be talking about in the next 3 lectures, if you had the food chemistry already. If not, it's going to be some repeat with a little more detail in here. That's a sturgeon. I caught that by jumping on it in the ocean. Okay? Literally. That's how I got it. It's a long story how I got to that point. Too many beers. Stuff like that. And that's used to be my boat. I had a big party with too many undergraduates on it, and we sank it. We hit an under the water log and put a hole in it, stuff like that. So that was the end of that. So, importance of moisture and water activity. Let's talk about that first, because I'll be talking about measuring moisture content today, and then measuring water activity and isotherms in the next 2 lectures. Very important in food is water. We have water in everything. And for some products, for example, grains, that grains have to be no more than 14% moisture. Okay? And there are devices that the inspectors have that they can detect the moisture content very quickly, and the price that you're going to get for the grain is based on a 14% water content of the grain. Fish meal can't be greater than 12%. And I didn't put it in there, but you might mark down that it should not be less than 6% moisture. So the range of 6 to 12%. Fish meal is a hazardous material. You have to have special barges for moving the fish meal from the Louisiana places where they make it up the rivers to Chicago or whatever. Lots of barges burn down every now and then, and that's because in hot and humid conditions, the lipids oxidize so fast, produce so much heat that it actually catches on fire in there. And when they first started moving fish meal from Chile to Europe, the first 50 boats that went across, half of them burned down at sea. And so it was a really difficult thing. I worked with one of the companies to try to solve that problem there. If it dries out, fish meal, if it dries out below 6%, that's below the monolayer. And if you remember from food chemistry, the oxidation rate goes up below the monolayer as well as above the monolayer. So that's why the range of 6 to 12 in there. So commerce, that's very important to know moisture contents. And usually you want to have rapid methods, and we'll talk about some rapid methods in there. We also have importance in terms of the stability, to know the water activity that controls microgrowth, it controls a lot of chemical reactions, controls texture, and then controls things like stickiness, caking, which are physical things. So knowing the water activity, knowing the moisture is a critical issue. If we do this, plot moisture content versus water activity this way, this is the type of curve that we're going to get. Above a certain moisture content, usually about 50% moisture, so 50 grams of water per 50 grams of solids on a dry basis, then the gain in moisture is not very much. I'm saying the gain in moisture is very large for a small change in the water activity. Strawberries, for example, 19 grams of water per gram of solids. Yeah. That's 95% water on a wet basis. If we plot it the opposite direction and we do a laboratory where we put products at different water activities, you remember that water activity is a small a with a subscript W. You're going to get, what, 20 points off if you write it a capital A? Microbiologists, if you're a microbiologist, learn that that's the wrong way to do it, okay? Typically, you get a curve that looks like this, a sigmoid-shaped curve. For many materials, if you take it from the wet state and bring it down, you get a different curve. Now, I've exaggerated it here. We call this hysteresis. And that says that the material has changed in its properties so that you get much larger amount of water held in the system on the way down. Technically, from a thermodynamic standpoint, at a given water activity, there's only one water content that is going to be in equilibrium. So that says that desorption is probably not in an equilibrium condition. There's something that's changed in the system in there. We're not going to go into that. So this just shows you a picture of something. Grapes, for example, 95% water, water activity about 9.7. Beef jerky, about 35% water, water activity of 0.8. My favorite food, gummy bears, a little lower in there. Soft texture. This is right on the limits up here of pathogen growth below a water activity of 0.84. You're not going to get the growth of any pathogens. You will get the growth of some molds that are carcinogenic, like Aspergillus flavus that produces aflatoxin. And then we have products that have two domains in it, raisins and cereal, rice and rye crisps in there. What is the problem with this cereal? From what standpoint? Yeah.
There's two different water activities. So
Yeah.
the cereal will pick up the moisture content of raisins.
Right,
And the raisins
yeah.
will dry up.
So the higher water activity, which is the raisin, is going to lose water to the cereal. There's usually they limit the amount of raisins so the cereal doesn't get too soggy because you want it crisp. But the raisins below a water activity of about 0.5, which will happen, they become little rocks in there, and people break their teeth on it. So that's a critical issue. There's ways to control that, but not all of them work that well in there. And then we have down here the typical classical snack foods that are very low water content and a water activity usually less than 0.2 in that range in there. So that's just an overall picture of moisture and water activity. So these are some paradigms. This, from a historical standpoint, the concept of water activity was in its infancy in the world in the 1950s. There was only two people who were actually doing something. They didn't call it water activity, they just called it equilibrium relative humidity. They didn't understand that it was connected to thermodynamic properties, but it was there. And one of them was a microbiologist, and he's the one who started the wrong statement that water activity is a measure of free versus bound water. It's absolutely not true at all. It has to do with the chemical potential. We're not going to go into that. Yeah. But just a list of things that it's related to. I'm not going to read through this list. You've gotten this in food chemistry as well in there. But these are paradigms that we came up with that helped us really change the way we looked at foods, in both wet foods and semi-moist foods and dry foods. So very, very important thing there. One of the critical things is that for intermediate moisture foods. Some products maybe 15 to about 30% moisture. Their water activities are generally 0.7 to 0.8, and that's the point, the water activity range at which the chemical reactions in food are the fastest. So above that and below that, the rates go down. But we like, marketing people like a lot of things that are in this chewy bar range, and there's a real problem there. We still haven't solved all those problems to try to prevent some of these reactions from occurring. So, if we're dealing with most foods, we're going to want to have a moisture sorption isotherm, so we make chambers that have different relative humidities. We put products in there, let them equilibrate in there. We take them out and measure their moisture content, and we can get that curve of moisture versus equilibrium relative humidity or water activity. Very simple thing. If it's a typical thing like a cereal, you weigh it in the beginning. You might measure the moisture content, initial moisture content, and then you weigh it at the end, usually 2 weeks in there, and you put it into some spreadsheets that you have. Do they have copies of the electronic copies of the spreadsheets or not?
We haven't sent them yet.
Not-
We
okay.
sent them.
Okay, good. Yeah. I've made spreadsheets so that you don't have to think in terms of calculating things.
They will think a little.
Hey, we'll think of it, okay. So, moisture content is sometimes done on a wet basis, so that's grams of water per total grams of the food. Very simple type of thing. Dry basis is the grams of water divided by 100% minus the percentage of water. So you're taking all the solids that's in there. And then non-fat, moisture by solids non-fat, you take the fat content out of 100%, and that's your water over the non-fat solids type of thing. This is used a lot in the dairy industry, the moisture non-fat basis. I'm going to skip over this statistics because you've had a lot of statistics already, right?
Yeah.
Yeah, so I don't need to do that, to talk about that, but I'll talk a little bit about precision of the instruments. The simplest way to do moisture content is to take samples, weigh them into pans, put it in a cabinet. And this has got, you can actually put 3 racks in here. Put it in a cabinet at a given temperature, some high temperature, and you hope there's some convection in there so that the samples dry out. And the AOAC, what does AOAC stand for? Anyone? Did you have this or not?
They should know it from first lecture.
From the first lecture? That's too far away. Right?
And if they're working on their projects, they would know it.
Association of Official Analytical Chemists is one way to say it. What do you say? What do you?
Association.
That's what, yeah.
It's communities now, not chemists. These are more than just chemists.
Okay.
Yeah, right. I didn't know that. And then the AACC, and now you got to put an I after that. But it's the American Association of Cereal Chemists International. Okay, so they added an I in it. They have set up standards. These standards are based on multiple laboratories working on the same product to measure something and to try to get what are some of the error bars in this and stuff like that. So, for example, for a given food area, they will have different time temperatures that you should use. Usually, you have to look for that category of food to find out which moisture measurement and what the time and temperature is. That way everybody does it the same way. But that assumes that all these little cabinets are the same, and they're not. Some of them have heaters on the top, some have heaters on the bottom, and you get some problems in there. Precision here is about 2.5% of the measured moisture content. So let's say if your moisture was 5%, and inaccuracy in this is 5 times 0.025 is plus or minus 0.125. And usually they round it up to 1 decimal place, so it would be about 0.2% on there. One of the questions is, okay, if we took this inaccuracy, our moisture content we measure would be 4.87 to 5.13. Is that important? Well, it is if you're going to be selling food as water, you know, or water as food in there. So it could make a difference. It depends on, with grain, it's not that important, that kind of difference in there. To speed things up, one can do it in a vacuum oven. So you have a chamber, again with racks in it, and then a pump, which is back here, that's pumping through. And we have this little thing here, dry ice, and it's like the pipe goes in, the pipe comes back out, and it goes into the pump. Why would we do that? Why would we put that there? What's coming out of the vacuum oven? Water. Water, right? And it goes into a compressor that's basically taking the water and squeezing it out from a low pressure to a higher pressure. And metal and water and movement causes rust. And so eventually your valves, which are basically veins in many cases, your rust, and you have to replace the pump. Okay, so this is dry ice, and you have the water condensing and building up inside here, but so it's not passing into the pump. That's a real critical thing in it from a standpoint of cost. By having a vacuum, there's less resistance to mass transfer and less thermal degradation, because now water boils at a lower temperature, so you can remove the water without going to too high a temperature and getting temperature effects on your product. So for example, AOAC says 26 to 28 inches of vacuum, 18 to 24 hours for meats. That's not AOAC for meats and other flesh foods. And for cereal grains, and this is AACC, you use a pressure of 100 millimeters of mercury, and it's only 5 hours in there. So that's much better than what we had on the previous page for doing things. So we need a vapor trap to save the pump. The problem is that the vacuum causes other volatile losses. And so if you're using some food plasticizers, like glycerol, propylene glycol, they will come off as well. So that creates a problem in that you shouldn't be using either a dry oven or a vacuum oven, because you're going to lose weight that's not going to be water there. And the problem with this oven and the previous one I showed you is that there's a thermal gradient in that cabinet. Depends on where the heater is. If it's at the top, it's going to be hotter at the top and cooler at the bottom. They don't usually have high-speed circulating fans in there, which would help solve that problem in there. And so you're going to get not only having pure temperature distribution, you're going to have moisture differences between the samples. And that's so what I suggest to people, use only one rack and put most of them as close together in the center of the rack rather than hitting the walls in there. And that's, people don't like to hear something like that because it's a pain. If I'm out on the plant floor and I'm checking on, let's say, cookies coming out of a large, long, maybe it can be 200 feet long baking oven. You know, and the cookies are moving down there, and you have as a control that it's got to be at a certain moisture because you don't want it either too crisp or too soggy. You're not going to wait the 5 to 15 hours in using a oven, so you want something fast in there. The typical instrument has a heater bulb in here, so it's an infrared heating bulb in there. The bulb is going to come about 1.5 inches above your sample. In this case, it was ground up popcorn in it. And so you run this at about 400 degrees Fahrenheit, so it only takes 2 to 4 minutes. But only one sample at a time, so it's best for things like dry powders. But what you need to do is you need to make a standard curve for the moisture that you measure here to what the real moisture is if you use one standard method that we were just talking about before. Okay, so that's a key. So it's good for QA, QC. It's not AOAC approved for measuring moisture. So you're getting a number here, and that number has to be in a certain range. That's all you care about in there, in terms of your standardization. The problem is that high temperature is fairly destructive. So products like, let's say, whey powder have protein and what else? What's in whey? Some people are intolerant to it.
Lactose.
Lactose.
Where's your $20 kid?
Huh? What?
You usually tell them, here's a $20.
Dollar bill? Yeah, no more.
No more.
I have a wife who likes clothes too much. So if you want a dress that's not been worn in 15 years, it's sitting there in a long rack about that long up there. You get the Browning reaction, Maillard reaction occurring, which causes problems, and the sample can burn at some point. So you have to be very careful. You have to standardize. You may have to change the bulb so you get a lower temperature to do that. And I just listed some of the companies that are out there. There's a lot of competitors in this area because it's a useful tool for quality control, but it's not the true moisture content of the product. Now you make it look really neat in there, and you can charge $5,000 to $10,000 for instruments like this, but that's all they're doing in there. I put the word accurately and reproducible, but that's accurate in terms of the standard that you're writing this for. Another one that's a faster one is an oven that also includes microwave heating. So you get better heating of the product than you do with a closed oven that doesn't have convection in it, because you're penetrating by waves into the product itself. One sample at a time, you put it on you're going to be doing microwave, right? So
Yep.
that'll be good. And you're doing convection oven as well? Okay. And what else?
Carl Fisher and
Vacuum, okay. So I got one more to talk about.
that you do.
Carl Fisher. And there's some new ones that have both the microwaves, but also some ultrasonics in it. That gives it even faster in there. What's your typical times in there for the stuff that you do?
For the microwave.
Microwave,
It's
2 to 5 minutes.
Yeah, depending on the sample.
Yeah, it would depend on the sample, yeah. Freeze drying. Here's a freeze dryer we have out in the pilot plant. What does a freeze dryer do? You can buy them, they're being sold on the internet now for $3,000, so that they, in their advertisement, they say that you can make food that's gonna last for 25 years. That's bullshit. Yeah.
It takes all the moisture and it goes straight from freezing and sublimates it to a gas.
Sublimation, right. You pull a pressure down in the chamber, so you're not sucking water out. What you're doing is lowering the pressure in the chamber, so you go below the triple point, which is 4.6 degrees C, and you want to get down into the frozen state. So generally, you either freeze first in liquid nitrogen, that's probably the fastest way to do it, and then you put it in this upper chamber here, and you turn on the vacuum pump, which is down there. There is a place where the water condenses back into ice in between there. It's in the back part of this. So the water sublimates, and then you have a high humidity there, and so the water is going to migrate to the cold surface and then freeze onto the cold surface. So very similar to what we saw with the trap, but we're doing it a different way, all internal in here. This is the most expensive way to do something. The cost of removing water in freeze drying is about $4 a pound of water. So if you wanted a pound of strawberries, 95% moisture, you have to dry out 20 pounds of strawberries, so you remove 19 pounds of water, and you have the 1 pound of strawberries, freeze-dried strawberries. Have you ever had freeze-dried ice cream? That was one of the things we worked on for the mercury capsules that were later on when they could actually get air. In both the Gemini and half the Mercury flights, there was no air in the cabin, so they had to wear spacesuits in there, and the only way they could eat was something that you could push through a little port here and bite off and chew on. And I forgot to bring it, but I've got one of the, a lot of the food was ground up, mixed together like mashed potatoes, beef, and some vegetables, then put into metallized toothpaste tubes, okay, and then sterilized, because had to sit around for a long time before they went on. And what they did to eat is they would pick up a tube that had screws, threads on both sides. You would take the toothpaste tube and screw it to one side. You take the other thing and push it in and screw it there because it had threads on the outside. And so then you put your mouth up against this thing that's sticking out that you're eating from, and you're squeezing this crappy food down there. They hated that. They hated that. That was terrible. You know, it was, but that was the first things we could come up with. And now they have much better food in space in there. But it used to be all dry with freeze-dried foods. Now it can be some regular foods that have a long enough shelf life. They're kept frozen so that you can cook from there. So typically, if you wanted to dry food in a freeze dryer, it takes about 75 hours, about 3 days. You're not going to want that in a laboratory. You know, some people do it because they like this kind of instrument, but it's not very good. You can also dry over desiccant. So the desiccants that you see, like dryerite in the laboratory, calcium sulfate, it takes at least 14 days to do it. You put it in a chamber, put dryerite in the bottom, and just wait. You can also do it with sulfuric acid solution. Put it in the bottom of a desiccator, again put the food in there, and the sulfuric acid will pull out the water from there. And then the third thing is drying over phosphorus pentoxide. It's a very, very strong oxidant. I don't know what year it was, but I was in on a quarter leave in Australia, and I get a call from the university waste disposal people. They had gone into the teaching lab where you guys have the class, and one person looked into the hood and they saw desiccators there that had samples in it, and these were basically things like propylene glycol, glycerol, things like that. We were drying them down because we were going to use them for controlling water activity, so I wanted to make sure there was no water in them. And we had phosphorus pentoxide in the bottom. That wasn't my idea, but it was one of my graduate students decided they were really going to get it dry. And it was labeled, so that was good. And the label said, on the desiccator, said phosphorus pentoxide. And they quickly looked that up, and it's supposed to be white, and it was sort of black, and it was sort of bubbling. Right? Well, what was happening, the glycerol was reacting, volatilizing, reacting with the phosphorus pentoxide, and it becomes very explosive at that point. So they called the Minneapolis bomb squad. Got everybody out of the building and took it to some place where they can ram it with something, and the things blew up. They sent me some pictures of it, which unfortunately I lost in there. But so don't use phosphorus pentoxide. So here's part of the problem of your sample. We talked about the problems of the equipment. Liquids can spatter, especially if you try to do it in a vacuum oven. So one way to do that is to, or if you're trying to do fats, same thing, you can add some dry sand to the product. That's going to slow things down, but that at least prevents the spattering, and you're going to get bad results from that. Some people cover it with a filter pad, but I think the sand is a better way of doing it, because that prevents the bubbling up of it. Grinding the product can cause some losses. In weighing, sometimes you get some losses depending on if it's a very light powder, sometimes things blow away when you're moving stuff. Now, why do we grind? Well, we have many times heterogeneous materials, different things in there, and so we want to get the whole moisture of the whole product. And so it's like a granola bar. It's a large, non-homogeneous product, so you've got to grind up the whole thing, and that creates a problem. We also have a problem is that some sugars, like lactose, can form a hydrate and bind very strongly to a water molecule. And so that causes a problem because you would have to go to very high temperatures to break that. The lactose monohydrate, you have to be at least 70 degrees centigrade to do that. The other is that amorphous materials like glucose or sucrose that may be in the product, they could flow above their glass transition temperature, and then they can trap water in the system. So that's a critical thing. Decomposition reactions, that's going to change the system, like non-enzymatic browning. In fact, non-enzymatic browning produces per glucose molecule that's reacting, you produce 3 to 4 molecules of water, depending on which part of the reaction is taking place, and that water is going to go off, but it's not water when it's in the food, so you get error there. Very important is the height of the sample in the cups. Let's say you're going to do triplicate samples. You don't just put stuff in the cups. You make sure you get the same height, because the drying time is a function of thickness squared, or depth squared. So if you had, let's say, 2 millimeters versus 1 millimeter of depth of a powder, the 2 millimeter one is going to take 4 times as long to get dry in the system. So that's a critical thing. I talked about other volatile losses like glycerol, whatever. Case hardening at high temperatures, especially with vegetables, as it loses water and the solid material heats up, it goes above its glass transition, and what you'll find is the material begins to contract and form a layer that reduces the volatility of the water. You can't get through it, and so you're going to get wrong results because water can still be in the product. There we go. The uneven heat pattern, which I talked about, is there. You want to make sure you cool the samples before you try to weigh them, because you're going to get heat convection in the balance, and you may not. You're impatient, so you don't wait until it stabilizes. So you want to cool it before weighing. I would do that in a desiccator or fish tank with dryerite in it, so you have a dry conditions, and it's not going to pick up moisture in there. So that's what's the last one here. So that's part of the thing. Okay, and here's just the formulas that I showed before of what dry basis, wet basis, and percent water is. And I'm not going to read through the equations, but that's there. So other methods, entrainment methods. So solvent distillation. Carnes was one of the first ones back in the 60s to come up with this method, along with Bidwell. It's an AOAC method. Basically, you put your sample here, and you add a solvent to it. You grind the sample, add a solvent to it, and mix it well in there. We used to use toluene. Now they use xylene. And unfortunately, both of them are carcinogens. And so most universities say you can't use either of these. And so the other thing that people have found is trichloroethylene. So what happens is the water will form a mixture with the solvent. They will co-distill at a given temperature, come up here into this condenser. They condense back into a liquid. So here we have liquid here, vapor here, liquid here. The liquid drips down. And this is a tube that has markings on it in terms of cc's. And so if you use toluene, it's lighter. So the water is going to form below the toluene. And with the trichloroethylene, the water will form above it. And so you keep on heating and heating and heating until no more is coming down, dripping down into here. And so you now have the actual cc's of water in there, and you multiply by the density of water, and you've got your water content. It was used extensively for spices. I don't know why in there, but a lot of spice houses would use this type of method today. We don't do it in the labs here because of the dangers of doing that. Another is to solvate it with, let's say, methanol, extract it in a flask, and then take a sample of the mixture after it's been sitting in the methanol, maybe overnight would be good enough with some stirring that's going on. And then you put it into a chromatogram instrument and measure by gas chromatography. And one company, Porapack, makes columns specifically for doing moisture in there. So basically the error bar here is about plus or minus 2% of the value that you get in there. Now solvation and chemical reaction, that's what the Carl Fisher method is. Okay? You react water with specific agents based on what's called the Bunsen reaction for measuring sulfur dioxide. So basically you have sulfite, pyridine, iodine, and water, which then reacts, okay, to produce hydrogen iodide. Okay, and further on, the reaction goes to this compound here. So you have iodine in there, and the iodine gets used up. And you can measure iodine by either color measurements or other ways. And the instrument you have is measures its stoichiometry from the standpoint of the current that flows in the system. There's a little grid in there, and they look at that, and it's very, very good. We call it a coulometric cell that does the measurement, and the range for these cells is somewhere between 10 micrograms of water to 200 milligrams. So very, very sensitive. So you have to estimate ahead of time what you think your range is going to be in terms of the amount of methanol that you're going to mix with the food in there. But it's very, very linear in that range with a resolution of 0.1 microgram in there. And nowadays you have your sample, you extract it overnight, and then you take a syringe, take a known amount of solution out of the flask. We usually weigh the syringe before and after. So we take the syringe, weigh it, suck the fluid into the syringe, squirt it into the coulometric cell, push the button, and it churns in about 5-10 minutes. Is it?
About 5.
5 minutes. You'll get the micrograms of water on the thing directly. So no weighing except for the syringe in there. And of course the weighing of you have to know how much methanol you used, and you have to know how much sample was used in the thing. So there is it's about 5 years old now, an alternative method where you dry the sample and capture the water vapor in the reaction vessel. I think that's a pain in the ass instrument. It doesn't work very well in there, so we don't do it. So this is what the instruments look like. This is the one that we're going to be using here with the coulometric one. A lot different. This one is the titration one. And one of the real problems now is they got very special fluids that you use, so you don't have to worry about it. In the days when you use the open titration for the iodine measurement, and you have toluene, or what is the other? Go back again. Oh, yeah. Pyridine. If somebody was doing the Carl Fisher by the titration method, you would know in 3 buildings down the block that you were doing, because this permeates the whole atmosphere in there, and it's a carcinogen. So we don't use that anymore in there. Problems is the extraction could be incomplete, bubbles in the syringe, and that's why we weigh the syringe before and after. So you don't have to worry about flicking out bubbles or anything, because you just go by weight. The methanol itself absorbs water, so you need to do a blank and subtract that for the methanol that's in your measurement. The solids in the solution corrode the electrodes, and that's expensive, and they do corrode over time in there because of the compounds that we have. And then the other one, which is really critical, is that under the conditions that the instrument works, the iodine can react with the double bonds on the polyunsaturated fats in there. And so the iodine disappears, and that's what you're trying to measure with the coulometric method or the titration method. And now you have, fat acting as if it was water in there to remove the iodine. So that's not good. Unfortunately, I didn't find a picture of it. It's one of my set of slides. The Alpha-Lux Speedy Moisture Meter. It's a British instrument.
So did you mention, I don't know if you did, but did you mention that with Carl Fisher, usually high moisture foods could potentially be a problem to measure with Carl Fisher?
Well, it's just the ratio of methanol you use. So with a high moisture food, you use more methanol.
So can you use like milk?
Yeah, you can. Yeah. So that you got to know the range for that coulometric cell. Okay, and I mean I put one set of numbers there, but different companies sell, and they have different ranges that it works in. So if you use more methanol, you know, and you grind up a piece of meat and put it in, you know approximately what the moisture is going to be.
Would the titration be just longer?
Yeah.
The procedure?
No, because you're gonna dilute it down so it's gonna fit in that range. So it's not too much difference on the titration, because it's a continuous titration on it, yeah.
Wouldn't you just use less samples so you're under 200 milliliters?
Well, you use less sample too.
Yeah.
But if it's a piece of meat, you don't wanna use too little of a sample because it's not, again, homogeneous. You know, so that you could pick a part that's mostly fat or a part that's mostly muscle tissue. So that's a critical problem. So one way around it is this speeding method. And this is very fast. It's a metal ball, hollow ball, that has a screw top. And on the screw top is a pressure gauge. So you can unscrew that. Okay? And you throw your sample into the ball, and then you take two pieces of, and did I say what was on it? Oh, I didn't say what, and now I forget what it is, but it's CaC2, calcium carbide. That reacts with the water and produces acetylene. And the calcium goes to the calcium oxide, and you got acetylene, which is this compound here. And you build up pressure in the chamber, because when you threw the carbide in, screwed it on, and waited about 10 minutes, and the pressure gauge is actually marked not in pounds per square inch, but it's marked in percent water in your sample. So it was designed first for cement, because if you're building something with cement, usually your state or your local have some very strict rules about the moisture content the cement can be depending on the outside temperature. So that's a critical thing, because otherwise you're going to get a building that crumbles during earthquakes, like just happened in Mexico. And there they don't have any regulations on the water content of cement. And now this company also sells it to nutrition laboratories, where you're going to be measuring the approximate value of a ground up mouse from a study, because you want to know the moisture content, the protein content, things like that. And so it's a nice, simple way of getting it done. But I'm not sure many people want to do something like that. So it's the Alpha Speedy Lux.
Okay.
Oh, there it is, there. Are we
Yeah.
done? And that's the instrument there for the cement.
Before you head out, you put G and H. Please tell me who is your captain next week. Come see me before you head out.
Oh, double bond. Oh, it should be double. Yeah. Yeah, no, that's huge.
It should be a triple bond, yeah. We don't have triple bonds on the typewriter.
Oh, I
Okay, so, yeah. Yeah, I forgot to, these are some old slides, and I corrected because I wrote it in myself. Yeah. Yeah, yeah.
For you, because I'm going back.
Oh, that's not mine. I didn't bring anything. Yeah, I'm taking Pam's. That's not mine.
Oh.
That's Pam's. No, all I did was bring this.
So only this?
Yeah.
Okay.
And my coat.
Okay.
It's when Jane.
Okay. Yeah.
Ted, don't walk out with my.
Oh, microphone.
Summary, is it the minimum that we need per ingredient? Like a